Perfect. Good evening, ladies and gentlemen. I'm Ronan Keane, Chair of Engineers Ireland Cork Region, and I'd like to welcome you to tonight's lecture. Our speakers this evening are Paul Griffin, Project Engineer with Irish Water Arvia, and Ross Henderson, Business Development Manager with O'Connor's Utilities Limited. And they'll be speaking this evening about the River Lee Estuary Crossing Horizontal Directional Drilling Project, which is a key part of the overall Cork Lower Harbour Drainage Project. The estuary crossing links the upgraded and expanded collection network in Cobh to that in Monkstown via trenchless installation of 2 number pipes. This then brings on to the wastewater treatment plant in Shanbally. So without further ado, I'll hand you over to Paul, who's going to speak first. Thanks, Paul.
Thanks, Roland. Thanks for that. Yeah, you can see that. Okay. I just want to say thanks to Engineers Ireland on behalf of myself and the project team just for this opportunity to share our project. As Roland said, I'm a project engineer with Arvia, Irish Water and the Major Projects Business Unit. I was overseeing the delivery of this Cork Lower Harbour Estuary Crossing Drill Project. Joined the project just before tender stage and saw through to completion. Now currently working as part of the team to deliver the Cobh networks, the northern networks, to complete the Cork Lower Harbour projects in the final part of it. So there's 2 speakers, myself and Ross Henderson from O'Connor's Utilities. Ross will take the second half of the presentation just on the technical aspects of the design as the chief designer of the horizontal directional drill and site operations. I'll just give you an overview of the project itself and how we got to where we did with the drill project. I suppose historically speaking, there's a map there of the Cork Lower Harbour network. The idea of the project was to capture all these various outfalls that are been discharging raw sewage and wastewater into the Cork Lower Harbour, kind of untreated for decades. So the Cork Lower Harbour project was to upgrade the existing wastewater network and capture all these outfalls and end the process of raw discharge into the harbour. Primarily focused on Carrigaline, Ringaskiddy, Shanbally, Passage West, Monkstown, in the southern side of the Cork Lower Harbour, and Cobh networks in the northern part of it. Also involved the construction of the Nerida wastewater treatment plant at Shanbally. All of this is to be in compliance with the Urban Wastewater Treatment Directive, which I'll talk a bit more on later. Just moving on, just some stats on the project there. So most of this is actually complete now, with the exception of the northern networks in Cobh and the green there, which is still ongoing. So we've been to Passage amongst them, as I said, the Shanbally wastewater treatment plant, Carrigaline, Ringaskiddy, that's all complete. So we've been kind of there since 2015, upgrading those networks. The estuary crossing link itself is shown there in the middle. There's a blue line just that's connecting from Monkstown over to the Cork dockyard to connect the southern and northern networks. Just for a bit of, I suppose, a bit of timeline on the project, the final pipe in the drilling project was installed on the 19th of March last year, just as lockdown started. So we were kind of fortunate in that event. A significant amount of civil works and disruption in the project overall for the last number of years. It's kind of essential to have good stakeholder management. And again, all this is aiming towards compliance with the Urban Wastewater Treatment Directive by 2021. So overall, the project was end the discharge of raw sewage, provide for an 80,000 P network with future-proofing kind of on the 25 to 50-year design horizon. It's cleaning up the harbour, kind of noticeable impact already is in the cleaner water that's there, comments from many residents as such. Just to enable the social and economic development of the area, and just to touch on the wastewater treatment directive. So that states basically that any population equivalent over 15,000 have secondary treatment of their wastewater in place by 31st of December 2005. Now, we're obviously a bit off that date. Many things have happened globally and throughout then. So the EU Commission did actually bring a case against Ireland to the European Court of Justice, with a hearing in 2018 and a judgment following thereafter against Ireland. Now, we were able to obviously show significant improvements across the country in various projects. We still have a lot more to do. Cork Lower Harbour itself, as long as it's fully operational by the end of 2021, it'll be deemed compliant with the wastewater treatment directive, and I'm happy to say that we're well and truly on target to reach that date, despite the restrictions that have happened in the last year. Just to summarise, there'll be 14 new pump stations, 27 kilometres of new sewers, 20,000 homes and businesses connected to the new sewage system. The equivalent of 40,000 wheelie bins of raw sewage had been discharged into Cork Lower Harbour. We're now roughly the equivalent of 10,000 still being discharged. Once Cobh networks are completed, we should have that down to 0 wheelie bins equivalent to raw sewage. 12 million litres of wastewater passing through the treatment plant in Shan Valley every day. The estuary crossing itself, there was many feasibility studies done on the most economical approach to connecting Cobh to the southern networks, or just having Cobh stand on its own. So the drilling project kind of became the most economically viable with least disruption to the shipping lanes, reduced the requirement for having additional wastewater treatment plants in Cobh. We just transferred the Cobh network down to Shan Valley treatment plant. This was done via 2 number 500 mil outside diameter rising main pipes with 426 litres per second kind of flow when operational, and 1.1 kilometre in length each. So there's 2 pipes going into the estuary. And discharge chambers then in the Glen Road and Monkstown and the R610 junction, and then tying into the existing sand key network that was upgraded as part of the earlier parts of the project. We also did a lot of removal of and diverting of overhead lines and cables in Glen Road. And this was at the time, and still is, the largest HDD undertaken in Ireland. So that's kind of where the project's coming from. The team itself then on the project, obviously Arvia is who I'm working for. We represent Irish Water. We do the major projects for Irish Water. O'Connor Utilities, the most successful tender. They're the main contractor, and PSCS. There was 16 tenders in the pre-qual stage that resulted in eventually 2 main tenderers in, and O'Connor's were deemed the most economically advantageous tender. It wasn't primarily on price. Many things went into that, including HSQE, their approach to comms, their quality management systems, their technical ability, and their ability to actually deliver the project. It was all fully reviewed, and they won the tender. Long O'Donnell are the NEC project managers. This is an NEC project, and they're brought in as the kind of experts on it, as it's a new type of project to Irish Water. It was at the time. Nicholas O'Dwyer, the NEC supervisor and technical advisor during the project. Before the project, they were the preliminary designers and the PSDP during the specimen design stage. They did a lot of the legwork on works information and getting this through planning up to the delivery of the project. Borges, our third-party consultant, they're experts in HDD, reviewing the designs and all that. So we just brought them in as an extra set of eyes and ears on the project, just to make sure we're all going in the same direction. And ASM were appointed as PSDP for the project. O'Connor Utilities won the project, so they're also the PSCS in the contract. It's a design and build project. So the design, procure, testing, commissioning of the not just the pipelines itself, but also the infrastructure around the pipelines, all the works to Glen Road and Monkstown, bringing them back to where they were, and in many cases upgrading the existing facilities that are available in Monkstown. Long O'Donnell then, they're deemed kind of experts in the NEC, where they have a vast kind of a CV behind them of NEC experience, whereas at the time we felt we were just too new to it to successfully manage the NEC project. It's a different type of contract to what we're used to, the major works projects and the FIDIC type projects. So that's where Long O'Donnell came to the fold. And as mentioned, Nicholas did a significant amount of work getting the project through the planning phase and up to the initial specimen design. And also, they were also reviewing all the design by Ross and OSU during the project. Just a timeline of the project there. So in 2015, the 4 agglomerations that were identified earlier that were in breach of the wastewater treatment directive had to be upgraded. We actually started works on Shan Valley in kind of July 2015. It was finished then in 2017. The estuary crossing project didn't actually sign until April of I think it was 2019, and successfully completed then by August the following year 2020. That's despite the impact of COVID towards the latter end of the project. So there was a small delay due to the lockdowns, but it was a successful project. We're currently now in the final phase of the project in Cobh networks, as I said, due to be complete this year. So initially there was a preliminary design that's gone back a few years that looking at various options of how to get Cobh networks and the northern networks over the southern connections. The initial design kind of looked at a crossing closer to the Glenbrook side of things, up where the ferry is crossing. It was deemed kind of not really suitable for HDD up there. We'd be looking at more kind of traditional methods of open cut and dredging. We'd be closing roads, closing the main roads very close to rail lines. We wouldn't be able to do a certain amount of SI that we'd need for reassurance before the project started. So it was kind of high risks, a lot of unknowns there, significant costs involved. So Nicholas Estuary brought in to kind of look at other options from a technical standpoint that would be better suited to this type of project. So a number of other options kind of jumped out. So the dockyard kind of, and the estuary crossing from the dockyard to Monkstown was kind of the one that was a clear winner really on all sides, technical, cost-wise and all that. Avoided the needs for extra wastewater treatment plants. The original preliminary design it just wasn't feasible. There were other options that just became more expensive as you looked at them. So I kind of narrowed it down to option one there, the dockyard to Monkstown. Then there was further assessments then to tie down the exact locations that would be most suitable for the launch site of the drill, but also the reception site where the drill will exit and the pipe, when it's being pulled through, will enter. Through the various assessment methods, there was a site located in the dockyard for the launch section, which almost allowed an almost clear shot over to Monkstown, coming up in the Monkstown Park on Glen Road, which is a kind of green area, heavy residential area, but it still allowed the drill to work. And there was also the Glen Road, which was ideal for stringing the pipe, because we had to bring 1.1 kilometre of pipe down the road twice. The lands up the top of Glen Road were ideal as well for the welding and assembly of the pipe. So again, the downside being it is in a residential area on the Sandkey, so there's a lot of risks involved in that too, which we had to mitigate. But the upshot, you can do the HDD drill relatively, I wouldn't say easily, but without too much issue, and you keep the main roads open in Monkstown Passage, Glenbrook area, and you're not really disrupting too much in Cobh. It's in a built-up area of wasteland in the back of the dockyard and not in a residential area for the drill itself. Here's just a shot from Monkstown Park. So that's the reception site there in Monkstown, just as it's being set up with the hoarding. You can see it's a heavily residential area next to tennis courts, a lot of amenities, shooting over and popping up there in the dockyard side of things. So the reception site, yeah, we did have to take over a park and basketball pitch. It was all returned in an upgraded fashion once complete with a new basketball pitch, a new multi-use sports ground there. They are built up areas, so the risks as well. We had a lot of we schools nearby. You have children, you have a lot of pedestrians, and from talking to the residents there, we knew there was a lot of cyclists would come down the hill at speed. So there were a lot of risks to the public in the projects which we had to mitigate against. There's also strict requirements in the works information for adhering to noise, dust, and vibration monitoring, which we were quite successful in the project. We do pre-construction surveys as well on all the buildings you see there that are surrounding it, just to kind of make sure that nothing was affected by the drill during construction and after, and post-condition surveys then confirmed that there was no impact. So just moving on then just to the option C contract. So as I said, it is an NEC target cost contract. It's a preferred form of contract for the HDD type. So it's kind of, we had to use it to be, I suppose, to be competitive out there as well, and to get the best kind of contractors for this job. It's a cost reimbursable contract, incentivization for the contractor. It's used in circumstances where the scope isn't sufficiently detailed. And in this case, there was a very detailed specimen design done, a lot of work done, but there's still a lot of unknown with HDD, and there's still a lot of site investigation has to be done, stuff that you just don't know about until you actually do the project. Things take longer. You're going through a kilometre of rock, kind of 60 metres below the harbour. There's a lot of unknowns, time taking, so it's a cost reimbursable model. The NEC is ideal for this. It's an open book, pretty much everyone's on the same page collaboratively. You share the pain and you share the joy in it. So it really did work on this project, and the result is that we did finish kind of within budget, hitting the milestones despite COVID-19 on this project. We utilize CMAR software as well on the NEC, which is kind of, it's the go-to software really for managing NEC type contracts. HSQE, so I won't go through each bit on the slide here, but suffice to say, we treated this project like a pharmaceutical project. So if anyone's worked on a pharma site, very rigorous, very heavy on the paperwork, on permits, on checking everything before anything happens to make sure it's safe, you know. So that really applied from the start here on this contract. Safety is above all else, and we kind of hammered the point home with the contract at the very start. It's constantly audited throughout the project. External bodies are coming on behalf of Irish Water, auditing projects. Happy to say O'Connor scored very highly consistently throughout the project. All design elements are workshopped in advance of design, and that includes getting the people who are actually doing the work in the workshop to influence design. Very often that's a step that's missed in design, where how it's actually done on the ground may not be as per the plans, but maybe better than the plans. So it's that constant process of getting everyone involved and getting everyone's input really kind of helps to deliver it. Nothing proceeded without design approval and HSQE approval, and that's very important, the HSQE approval as well. Things take a little longer that way, but there's the kind of the safety aspect of it. You just can rely on it. You can sleep easy at night knowing things are going to be okay. We did have iterative lessons learned via the workshops. So there was 2 drills done. We were able to learn from drill 1 what worked, what didn't work. We adjust methods for how drill 2 was done, how the pipe was pulled down. We saved significant amount of time off construction as well in the second pipeline by learning from the first one through these workshops. In all, there was about 110,000 hours worked on the project, 627 site inductions. There was no near misses and 1 minor first aid where someone cut their finger on the project. That was all in the high-risk project, and I think that's a phenomenal achievement. As such, O'Connor Utilities actually won the Major Projects Inaugural Contractor Safety Award this year because of their commitment to health and safety. So a big success in that regard. Another aspect is the stakeholder engagement. So you can see that, like, we are right in front of people's houses. They can just almost walk out and look at the site. In the picture, you can see the pipe that's actually coming down the road. So what you don't see from the picture is how steep that hill is in Glen Road, and that's a 60-ton pipe coming down on rollers. So engaging with the community on the dangers of the project, but also on the benefits of the project and keeping them informed. We told them right from the start, it's going to be in your face, it's going to be a disruptive project. We let them know what's happening all the way in advance, so there's no surprises. And in general, they're very positive with that approach. They like to be kept in the loop, and it works. You keep them informed via text mailing lists, with open days, constantly calling to their houses, making sure everything's okay, listening to feedback. There was no significant complaints in this project, despite the nature of it and being right in front of people's houses. You find that the residents are kind of very supportive of the project by the end of it. In addition to kind of the talking just to residents, we also did a lot of other things beyond that. We went into school visits. We talked to kind of the 5th and 6th class in Sculbar and Afa there in Monkstown. Great opportunity. You should ever take it if you get the chance to go in and visit a school and promote a project. They'll really grill you on it. During school drop-offs, we would stop machinery so kids could be dropped to school safely by their parents. Here's a picture from the Hazelhurst Gallery in Monkstown, who were very supportive of the project. Actually took a piece of the pipe and did a display about the project. So we did have a significant amount of feedback and support from the community. And again, this is all down to O'Connor Utilities' approach to stakeholder engagement and their communications, which was their communication management plan, which was part of the tendering and qualification process, that they could show a significant kind of professional approach to this. And just to end it off, so there was another small little thing we did kind of for the stakeholders at the end, just getting the kids involved. Just during the pipe pulling event, we were going around just giving them little children's packs of goodies and stuff to get them involved. And you see little kids there wearing the O'Connor's high-vis, you know, there's just residents there in Glen Road who were just happy to support the project and kind of see a feat of engineering go into the harbour. So that's all from me just on the intro to the project, and I'll just hand you over to Ross Henderson there now.
Okay, Paul, thank you very much. This section of the presentation is about the HDD itself, and it's split into two parts. The first part will be about the design work that we undertook prior to the works, and then I'll present a section on the actual drilling itself and some of the issues that we encountered during the drilling. The first slide here, I'm aware that not everybody on the webinar this evening is out of the pipeline industry. So just to talk a little bit about horizontal directional drilling, HDD, and the concept. It's different from most other trenchless technologies such as microtunneling and auger boring and pipe jacking in that it's surface launch, surface receive. We don't require shafts or confined space working or dewatering to launch the directional drill. We drill from surface to surface. And the drilling string is pretty flexible. So it's designed to go around corners. Again, unlike auger boring and pipe jacking, which are designed to go in straight lines. So the first picture here, we start off with the drilling rig, and we drill a small diameter pilot hole underneath the obstacle that we're going to cross and back to surface on the far side. We then remove the pilot hole drilling assembly and we pull 1, 2, 3, a series of hole openers back towards us, enlarging the hole. So each hole opener will be larger than the previous hole opener until we have a hole that's large enough to accept the pipeline, and we then pull the pipeline back in towards us. So that's the general concept of directional drilling. Now this slide shows the feasibility study that Ervia had conducted, and this was the stage at which we came into the project. You can see the Cork Harbour down here on the east side and drilling a shallow horizontal curve across to the playground at Monkstown on the west side of the harbour. Now, as Paul has said, the idea was to transfer the sewage from the east side of the harbour into the network on the west side of the harbour. So the feasibility study had us drilling these two bores into a manhole on Shore Road, so that we could discharge directly into the network on the west side of the harbour. You can see this manhole here. It's 8 meters in diameter and it's 15 meters deep at the point where we were to intercept it. Now that's quite an ask for directional drilling. If you look at the tolerance of the guidance systems, they're certainly capable of hitting targets that tight. But you know, we're drilling in 3 dimensions, so not only do we have to have the orientation of the drill correct, we have to have the depth correct and its inclination as we drill through these soft eyes that would have been cast into the casein. And although the steering tools might be capable of measuring accuracy to the tolerances required, it doesn't necessarily mean that we can drill to those accuracies. There are a lot of other aspects that come into play. It's a bit like saying I've got a car that has a top speed of 120 kilometers an hour. It doesn't mean that you can drive from Cork to Dublin in 2 hours. There are other things that come into play. Primarily the geology you're drilling through. As I say, the drilling assembly is flexible and is designed to go around corners, and it has a propensity to do so. So a lot of the time we're not positively steering the drilling assembly. We're making corrections and bringing it back online. So we were a little concerned about the accuracies required for drilling. And the concept we came up with at design stage was to drill all the way into the children's playground on Glen Road, and then pipe the sewage stream back down pipelines open cut in Glen Road, and to intercept the network on the west side of the harbour at surface here. That gave us a lot larger target to aim for in the park at Monkstown. So once we were happy with the concept and what we were going to be trying to do, we had a look at the geology. And in Cobh Harbour, the ground is made ground at surface, overlying alluvial and glacial deposits. At Monkstown, it's all alluvial and glacial material overlying the sandstone bedrock. There's not really much difference in the bedrock across Cork Harbour, perhaps slightly more siltstone on the west bank. But what is lying in the Lee River, and most rivers will flow and erode their way down into the bedrock in the areas of weakness, there's a major fault runs up the Lee Valley. And faults always concern us when we're trying to drill through them, because they often incorporate broken material, fractured material, fissures in the ground where you can lose drilling fluid into the formation. So we were concerned about the faults that we might come across in the middle of the harbour. There had been quite a bit of site investigation done at feasibility stage, and we knew that the top 10 meters of bedrock was very weathered and broken, and we would have to be at least 10 meters into the bedrock to drill in hard, competent formation. So this is the HDD bore design we developed. And looking at the plan view, if you recall, the feasibility study had a shallow curve from entry to exit. We didn't want to be drilling a horizontal curve and trying to gain vertical angle at exit. So we tightened the horizontal curve up and moved it all out into the middle of the bay here. So we drilled in a straight line underneath Cork Harbour, then implemented the horizontal turn in the horizontal section, and then we were able to concentrate on building angle and coming up out of the ground at the target exit points in Monkstown. There were one or two other criteria that we had to take into account. The harbour wall at Cobh is held together with anchor ties back into the made ground. So we had to stay well beneath them. We can see we're 50 meters below the anchor ties here. We're 58 meters below the harbour wall, and we're 30 meters below the bed of the River Lee at the deepest point. Because we're drilling two parallel bores here and we have a horizontal turn to put in, we designed this section where we're making the horizontal turn to separate the bores vertically as well as horizontally. At entry point in Cork and Monkstown, the two bores sit side by side, but out here where we're trying to make left-hand turn, we separated the bores vertically so that the second bore that we put in would be the lower one, and if we weren't quite able to make as much turn as we'd anticipated, because, for example, we run into a soft patch of ground, then there was no risk of the inner bore bumping into the outer bore. So once we were happy with the HDD bore profiles and the geometry, we undertook settlement calculations to work out what the impact on the rest of the environment was going to be by the drilling. Now, settlement calculations are all done on a worst case scenario basis. So we calculate for the entire annular void collapsing, and then that entire collapse migrating all the way to surface. So that very, very rarely actually occurs in a live environment, but at least it gives you an idea of what the worst case scenario might be. And of course, as we have two bores here, each bore has its own settlement trough plotted at surface, and we have to calculate, add them both together to calculate what the total settlement might be. So we did these calculations for every 25 meters along the bore and for all the critical infrastructure. So crane rails in Cobh docks, 2.3 millimeters potential settlement. The harbour wall at Cobh, 2.79, and then on the Monkstown side, the Monkstown quay wall, the Strand Road. We drill underneath the garden of a private residence, so we calculated the settlement for his two garden walls. And then as you come out of bedrock, the calculation changes a little bit because you're not calculating for cohesive rock, but we're calculating for cohesionless glacial settlement. So you jump up to a potential 17 millimeters settlement, but that is within the playground at Monkstown and relatively close to surface. So as part of the condition verification, we did a survey of all these critical points. We installed noise monitors and vibration sensors on all the critical points, and we had divers inspect the quay walls at Cobh and Monkstown so that we had a precondition survey should there be any movement or vibration during the works or after the works. The next aspect of the design we looked at was the stress we would impose on the pipeline, pulling it into the bore. Now, if we pulled this pipeline into the bore empty, it would be buoyant because it would float in the drilling fluid and drag on the high side of the hole and exert quite high tensile forces. And we have to consider not just the tensile forces on the pipeline, but while the pipeline is under tensile load, its ability to withstand hoop stresses and buckling stresses and collapse stresses is significantly reduced. So it's a big aspect of the design is to make sure that the pipeline can withstand the installation forces. So to stop the pipeline being buoyant within the bore, you can preload it with ballast to reduce its flotation. But that, of course, makes the pipeline that's still out on land during the pullback very heavy. So the technique we used here was to provide a tow head with ports in the front of it. And just in the lead section of the tow head, we cut slots in the side of the pipe, you can see here. So as we pulled the pipe into the bore, the drilling fluid in the bore flowed into the pipe and reduced the buoyancy of the pipe. But the tail of the pipe that's still hanging out of the ground at Monkstown, that hasn't got any fluid in, so that stayed light enough to pull down the hill. So with these calculations, we figured that it would take 34.5 tons of pull force to drag the pipe in. The solid pipe has a tensile strength of 79.4 tons, nearly 80 tons. It's SDR9 pipe, so it's a pretty thick walled pipe compared to most water pipelines you'd lay conventionally by open cut methods. The tow head with the slots cut in the side reduces that tensile strength down to about 63.5 tons, but still twice the anticipated pull force. and we have the swivel and a shackle that connects the tow head to the drilling assembly that are rated at 250 and 75 tons. So the drilling rig we specified, this is a 400-ton unit. Drilling rigs are rated depending on their push and pull capacity. So a more powerful rig has more push to drill with and more pull to install the pipeline. So a 400-ton rig has the ability to push 400 tons and pull 400 tons. The drilling assembly here, we have the drill bit on the end, and behind the drill bit, we have a drilling motor. Now, there's a drive shaft in here. It's a bit like a turbine. So as we pump the drilling fluid down the inside of the drill string, it spins the turbine, and the turbine spins the drill bit. We don't rotate the entire drill string all the way from the rig. And there's a shallow bend here in the motor. It's only 2 degrees. So the drill bit is offset to the axis of the drill pipe by 2 degrees. And we put a steering tool behind the drill motor so we know if this drill bit is pointing up, down, left, right, or anywhere in between. So we orient the drill bit in the direction we want to drill in. So if we want to drop angle, we rotate the motor until the drill bit is pointing down. Then we start pumping fluid through the motor. The drill bit starts spinning, and we just slide the drill pipe into the hole without rotating it, and the drill bit will drill an arc down into the ground. When we want to come back to surface or turn left and right, we stop and we reorient the drill bit in the direction we want to head in. So the drill bit is obviously integral to the drilling action. And they're quite complex pieces. This is an oil field drill bit, a tricone drill bit with 3 rotating heads on it. And they come in an infinite number of different styles. And it's important to match the drilling structure on the drill bit with the formation you want to drill through. If you're drilling in soft formations, these teeth would be very pointy, very aggressive, and they would drill soft formation very quickly. But in hard sandstones, they would wear out very quickly, and you'd have to keep changing the drill bit out. If you're drilling in very hard formation, you would have very small dome-shaped cutters that would have great life expectancy, but they drill a little bit slower. So it's important to match the drill bit with the formation that you're anticipating. So the sandstone that we were drilling through, we expected it to be at its hardest 53 MPa. Again, this is from core samples taken across the harbour and analysed in the lab. And we selected an IADC Series 5 bit to drill these formations the most cost-effective manner. You also have to match the drill bit with the downhole motor. Different downhole motors convert the hydraulic power from the fluid stream into RPM and torque at different ratios. So some motors will spin at high RPM but low torque, and some motors will spin with low RPM and high torque, and that's the motor that we selected for this job, a low RPM but high torque 3-stage drilling motor. And after the pilot hole, we designed the hole opening passes in 2 passes, a 23-inch pass and a 28-inch pass. The fluid pump, this is an oil field cement pump, Halliburton pump. It's capable of pumping up to 600 gallons a minute to flush the drilled cuttings out of the bore. Let me go back one. And this is the mud mixing station. The drilling fluid is supplied as a dry product. It's mixed with fresh water in a hopper here. The drilling fluid, the water is treated with soda ash to raise the pH initially, and then we dose the bentonite drilling fluid with a little biopolymer to raise the gel strength. The drilling fluid's actually quite complex. It's referred to as mud on site. But what we're trying to do, it performs a number of functions. It cools down the downhole instruments, it lubricates the borehole, but it helps stabilize the bore, but its principal function is to carry the drilled cuttings out of the hole. So every time we stop drilling after a joint of pipe, every 9.5 meters, we have to add a joint of pipe at the rig. So we have to stop pumping. So we need the drilling fluid to suspend the drilled cuttings, otherwise they sink to the bottom of the hole. And of course, we're only drilling a 12-inch hole. So where it's horizontal, those drilled cuttings only have to fall 12 inches before they start building up a bed on the low side of the hole, and then they're very difficult to get agitated and back into suspension. So we want that drilling fluid to gel very quickly to suspend the cuttings, but at the same time, we need to get it flowing again with very low pressures. So you're trying to develop a drilling fluid with very high gel strengths, but very low shear strengths, which is quite complex. So it's a very intense part of the drilling operation, is maintaining the drilling fluid parameters. The other aspect of the drilling fluid is the downhole pressures. So we calculate what the theoretical drill pressures are. Here on the x-axis, you've got the length of the bore from 0 to just over 1,000 meters. And you've got the mud pressure in kPa on the y-axis here. And this green dotted line is the downhole pressure you expect the fluid to be in the bore. So you can see as we start at surface, pressure increases as we build depth. And then in the horizontal section, it increases slowly just due to the additional length of bore and the friction of the fluid flowing back along the annulus. And then as we come back to surface, the downhole fluid pressures reduce again, because in effect you have a U-tube down there. And the red line is the fracture gradient. That's the pressure at which we expect the formation to fail and the drilling fluid to flow into the formation rather than back up the annulus to surface. And again, you see it follows the bore profile. It increases with depth and then comes back to 0 as we drill back up to surface. Now you can see for the most part that pilot hole mud pressure is well below the fracture gradient. But as we get back towards surface, where we're pumping 400 gallons a minute of solids laden fluid over a kilometer back along a 12-inch hole with a 6 5/8 diameter drill pipe in it, that pressure in the annulus exceeds the ability of the formation to contain it. So we were anticipating what we call breakouts as we approached the park at Monkstown, where you start to lose drilling fluid into the formation and it can come up to surface as an inadvertent return. This is the fluids recycling system. All the fluid that comes back to surface, we clean through the recycling system. We have a series of 4 shaker decks here and 3 sets of hydrocyclones that removes all the drilled cuttings and allows clean fluid to drop into the tank underneath the shakers here, and the clean fluid we reuse. So it minimizes the volume of fluid on site, and having a minimal volume of fluid on site, we can see changes in that volume very easily. So if we start losing fluid into the formation, we can see the levels in these tanks dropping. And conversely, if we start gaining groundwater from the formation, we can see the fluid levels start to rise. So that's the concept and the design stage completed. These next few slides are about the actual works and what happened on site. So first of all, we arrive at Cork dockyard, and it had been historically a bit of a dumping ground for waste materials. So we had 4,000 cubic meters of material to remove before we cleared the site. and made it available for rig up. One of the potential issues that we were concerned about was contaminated land. Some of the boreholes that had been done during the site investigation in Cork Harbour encountered contaminants. Once we'd cleared all that waste material from this area, we were able to drop a site investigation borehole and confirm that there wasn't any contaminated land there. We had planned to put in a big surface casing. We'll come on to that shortly, but we were able to reduce the surface casing because there was no requirement for protecting the polyethylene pipe from potential hydrocarbon contamination. Now, the drilling site here, plenty of room. It's about 50 meters by 50 meters. You can see the proximity to houses. These houses, we put noise sensors up around this estate so that we could make sure that we weren't causing any overdue disturbance to the residents. And as I said when I was talking about the mud, we mixed the mud with fresh water. The harbour is obviously salt water, so we dropped ourselves a water well in the corner of the site. You can see the bund in the corner here, where we had a little lagoon to keep ourselves a buffer stock of fresh water. The site setup, you've got the drilling rig here. Obviously that is dictated where entry point is. The tie-in point is actually out here. It's a depth of 4.5 meters below the surface. So we back calculate entry point based on the future tie-in point within the pumping station. There's a hydraulic power pack here that powers the rig. Cabin 3 is the drill cab that the operation is run from. 4 over here is the mixing unit. 5 is the pump. The fluid comes back up out of the annulus to the holding pit here. 9, the entry pit, and is pumped up to the recycling system. The lagoons here, item 7 is the slurry and the drilled cuttings, and 8 here is tools and laydown. You can see we've arranged the site. This is the noisiest piece of kit we have. This is the generator, and we've tucked that away behind the recycling system to provide a buffer between the noisy generator exhausts and the residential houses at the top of the photo. So this is looking from behind the drill rig, looking down the center line of the bore. We drill away from the rig. Underneath, you can see the overhead cranes here in Cork Harbour. We drill under the crane tracks underneath the harbour wall and across the harbour. That's the Monkstown harbour wall on the far side, and up into the children's playground. We pin the rig down with a sheet pile. It's critical that the rig doesn't move once you've got it on site, because you're threading these connections, the drill pipe together, to prevent any cross threading of those drill pipes. The pipe in the ground has to be aligned with the rig, so it's critical that the rig doesn't move during the works. And here's the surface casing we did put in. We just ran a 16-inch surface casing. As I say, we were able to confirm that there wasn't any contamination in the ground, and that the made ground had a lot more clay content, was a lot more cohesive than we'd anticipated. This is the exit side in Monkstown. Before we arrived on it, you can see the basketball court Paul talked about at the top end, then a football pitch, and then the children's playground at the bottom end. So we'd taken over the football pitch and the basketball pitch here. The first thing we had to do was gain access to that site for some pretty substantial plant. So we built a culvert across Glen Brook that enabled us to get all the equipment off Glen Road and into the exit yard. This is quite a small exit pad for an operation of this size. It's only 25 meters wide, 80 meters long, so there's plenty of length, but it was quite constrained, and having to bring vehicles in at the front end, driving over where the exit points were going to be here was quite tricky. It was an aspect of the operation that required a lot of management. Similar setup for the fluids handling. Of course, once you punch out with your pilot hole and start the reaming operation, as the reamer goes in from exit side, all the fluid that you're pumping down to clean the cuttings out of the bore are appearing out of the ground at exit side. So we have a similar recycling system here to clean the fluid, and then a pump to pump the fluid back into the drilled string at exit side through a swivel. Again, the recycling unit here, close proximity to residential houses. So we encased it in a scaffold with noise suppression blankets around it, and hung noise suppression blankets, acoustic blankets on the fence of the tennis club to reduce any impact we had on people playing tennis. This is the center line looking back from exit, the Cobh dockyard in the on the far side of the harbour there, entry point over here. Now the geology, as I say, we'd anticipated potentially coming across this F5 fault in the middle of the harbour here and potentially encountering broken fractured rock and fissures. In actual fact, in the eventuality, we didn't really see any broken material here, so that was a bonus. What we did see was a slowdown in the rate of progression as we drilled through this faulted zone. And what we think has happened is there's probably some secondary mineralization in there of maybe chert or quartz that was more abrasive and harder to drill. But apart from that, we didn't really have any problems with the geology at all. This is exit point. You can see that red circle painted on the ground there is the target we're aiming for. And this is the drill head on the first bore coming out of the ground. So you can see there's a 30 centimeter diameter drill head. The center of the drill bit was 26 centimeters right of target on the first shot. The second shot, we were 21 centimeters left of our target. So after drilling for over a kilometer, I think that's a bullseye in my book. You can see here the ROP figures. The red line is our planned rate of progression, and the green line is bore one. You can see when we got up to about 600 meters here, we were above the timeline, but then we slowed down drilling through the fault, then picked up pace again. But then as we came towards Monkstown, we slowed right down. We did see a little bit of breakout of drilling fluid, so we stopped for a couple of days to clean that out. And we were very careful coming to surface the first time, just because of the concerns of potential breakout. The second shot, the blue line, quite a similar rate of progression, stayed above the planned drill line, again slowed down as we drilled through the fault zone in the middle of the harbour. This time we were a lot more confident of the ground coming towards surface, and because we already had one bore in, the first bore acted as a conduit for fluid to surface when we were drilling the second shot, so we were able to punch that out much quicker. These are the drilling tools after the pilot holes. This is the drilling motor. You can see that bend in the motor a little bit clearer there, 2-degree bend. And here's the drill bit. We drilled this with one drill bit, so still quite a bit of life left in that, although there was uneven where you can see this heel row of tungsten carbide teeth have all been completely stripped from this cone. And what we think has happened is we've got some junk trapped in here in the middle of the bit. And as this cone has rotated, we've torn off the TCI teeth on that outer row. So the hole opening operations, The hole opener here is put onto the drill string. We pull that back into the bore. We use a tong hand to make up all these connections. These connections were always a very dangerous part of the operation. The drill string is being rotated by the driller who's sat in a cabin over a kilometre away, and we have to line these pipes up and rotate them and torque them up. And it was always very dangerous to have manpower involved in that operation. But this tong hand has taken all the manpower out of the operation. It's a one-man operation. He sits in the cab. The drill pipes are all aligned. They're torqued up to the correct torque. And it's a much quieter operation because we're not bouncing drill pipe around on the end of strops. The hole openers, this is what it looked like going into the hole. This is the 23-inch hole opener on the first run. We came to a grinding halt about halfway through the bore. So we pulled it out and discovered that the teeth on the cutters, you can see here, they've almost entirely gone. We don't think we were pumping enough fluid to flush all the drilling cuttings away from the hole opener, especially drilling through that mineralized fault section. And I think the hole opener was just sat there spinning in a porridge of abrasive material. But the tools were able to replace the cutters on site and run back in and complete the bore. The weather, I would normally say that the weather doesn't have an impact on drilling operations. But if you recall, February 2020, we had Storm Ciara come through, an extratropical cyclone. And then a couple of weeks later, we had Storm Dennis, something the Met Office referred to as a weather bomb that dropped a month of rain in 24 hours. Now, we were aware that Glen Brook that runs down the side of the Monkstown site now, if you look at the historical maps of the location, that brook has been realigned to make room for the football pitch in here. And what we think has happened, the former channel for Glen Brook was potentially acting as a pathway for groundwater, and it was distributing it into the bore. So what we did was we brought back our site investigation contractor and we dropped a couple of interception bores here to abstract groundwater. The groundwater that was getting into the bore, it was diluting the drilling fluid. It was dropping the gel strength, and we no longer had the capacity to flush all the cuttings out of the bore. So it was quite a serious issue for a couple of days until we got it sorted. So you can see again, here's the rate of progression curves for the 23-inch hole opener, the green line. This is where we pulled it out of the bore and replaced the cutters. So for the second shot, rather than run the 23-inch, we did it in two stages. We ran an 18-inch hole opener and then changed that out and ran the 23-inch hole opener to finish the bore. So doing it in two passes took us a day longer than doing it with the one pass, but we did have a couple of days in here. You can see this is where we had the groundwater issue and had to stop the drilling while we resolved the drilling fluid issues. The 28-inch hole opener passes, they went a lot quicker than we planned. We ended up about 6 days ahead of the curve on the second hole opening pass. So just quickly, the last aspect of the project is to fabricate the pipeline and to pull it into the bore. So you can see the two bores are the red lines at the bottom here. The nearest fields to Monkstown where we could find enough room to string the pipe out was at the top of the hill, over a kilometre, 1.3 kilometres away. So once we'd fabricated the pipeline, we had to pull it down Glen Road so that it was ready to be pulled into the bore. The pipe was all factory acceptance tested. We went over, it was specially made for the project in Germany. We went over to Germany and inspected all the quality in the factory, and then there was a site acceptance test with every joint of pipe that arrived. We had ourselves a welding station here. And we built ourselves a semi-permanent. Often you see butt fusion welding being undertaken in tents. Now, because of the size of the project and the fact we were working through the winter, we built ourselves a proper steel shed, and with the two storms, Kiara and Dennis, coming through that we hadn't anticipated, it was just as well we did. We were able to continue welding through those tremendous storms. The welding all done to DVS 22071, and all the welds are inspected, and then there's a random testing procedure as well. 1 in 30 welds are cut out and sent away for independent destructive testing, and we had no failures at all on the welding process. All the welds are numbered for traceability. The welding data is recorded from the automatic welding machine. The internal beads are removed, as well as the external beads, and twist tested on site. And the internal beads are CCTV inspected to make sure that the beads have been removed and the weld looks good on the inside as well as the outside. We move the pipe around with these power pushers. They're hydraulic grips that grip the outside of the pipeline without causing any damage to it. Using the excavators with these grips on, you can't slew the grip sideways because you'd be moving in an arc. So what we do is we build platforms and put a culvert under there and park the excavators up on top of the platform, and it pulls and pushes the pipeline towards or away from it, depending whether we're pulling pipe away from the welding station or pulling it across the ground. You can see the welding station here, and the welded pipe strings run out to the top of the photo here and then turn left across a stream and out to the left-hand side of the fields. We put access tracks in here so that we could get vehicles in and out for refueling, etc., etc. You can see where the access tracks ran over the pipeline strings. Again, the pipelines are culverted through underneath the platforms. Now, to move the pipe from the welding area down Glen Road, you can't just tow it down the road, because if it was in tension, it would want to straighten out, and we've got a lot of bends to get that pipe through. So we brought in this pipe pusher, which has hydraulic wheels that clamp down onto the pipe and then rotate. And we push the pipeline out of the fields into the road. And you have an excavator here, and all that does is guide the head of the pipe down the road as the pipe pusher here is pushing it out into the road. We calculate where all these rollers are going to go and pre-position them. There are spray up marks on the road. So just before the pipeline arrives, we lift the pipeline rollers out into the road and lay the pipeline on it. So we move the pipe down the road the day before pullback. Where we're coming round corners, you can see here we've got 2 rollers, one horizontally and one vertically, and we have a couple of 1-ton concrete blocks stabilizing those rollers, and that just helps to guide the pipeline as it's coming down the hill. But remember, it's being pushed down the hill, not pulled down the hill. There's a couple more slides here just demonstrating the rollers and the layout of the pipe. You can see the slots in the tow head on this one for allowing the pipe to fill with fluid once it's in the bore. Coming down, again, there was a lot of liaison with the local residents, making sure they knew what was happening and the timing of the works. You can see it comes down through quite a number of houses here. I like this photo. You can see on this side of the stone dike wall, you've got 100 tons of polyethylene pipeline being towed down the road, and on the other side, the golfers are still able to play golf. We built 2 footbridges over the pipeline. The residents all had contact phone numbers. If they wanted to get in and out of their houses, they were escorted from and to their houses. And we had a golf buggy running up and down the road at the side of the pipeline that carried their shopping and carried them if they couldn't walk the distance. And we used the car park at the local golf club for them to park their cars so that they could get in and out to work and to the shops and to whatever else they wanted to do. This is the pipeline coming down Glen Road. You can see how close it is to the houses here. And then we lifted it over Glen Brook and over the site hoardings using 3 pipeline cradles. It comes over, down, hooks up to the hole opener and gets pulled into the bore. And both pipelines went in with about 25 tons pull force, so quite a bit less than the 34 tons we'd estimated. Very smooth bore that the drillers drilled, you know, very little tortuosity in it, nice and slick, well lubricated, very good job. For the second pipe pullback, we actually moved the pipe pusher. We pushed the pipe out of the fields using the grippers, and we put the pipe pusher halfway down Glen Road. It just for ease of operation, and enabled us to hang on to the tail string coming out of the fields. The other aspect of the second pipe pull that we had to deal with was COVID-19. You can see the guys had to socially distance for the pipe pull, and it did mean that all the kids were off school and the parents were at home from work, so we had quite an audience for the second pipe pull. But I think that's my last slide, but one. So 2 500 mil SDR9 pipelines across Cork Harbour, the 2 longest drills in Ireland, 1,025 meters and 1,028 meters. My email address is there. I know we're going to take some questions here. I know we're getting late, so if you want to scribble down my email address and find me questions that you think of after the event, I'm quite happy to answer questions after the event. Thank you very much.
Thank you, Ross. That was excellent, and Paul as well. Very, very interesting. I actually had the pleasure of visiting the site, I suppose, before the COVID restrictions kicked in properly. It was great. It's great to see a project like that being done on our doorstep. It's I don't suppose we're likely to see something similar in Cork again for some time. So look, folks, as Ross said there, we will take questions. You can see at the bottom of your screens there, there's a Q&A button. So if you want to pop your questions in there, and Ross and Paul can take them. So I see a few of them popping in there, so I'll just read out the first one. Paul and Ross, if you want to, you can view them as well. So the first one's from Padraig O'Keefe, and he's asking, is the method of allowing drilling fluid into the pipe to reduce buoyancy possible on potable water mains? I assume this would be a water quality issue.
Yeah, I'll pick that one up. Yes, absolutely. This is obviously a sewerage pipe, so it didn't matter that we had dirty drilling fluid filling the pipe. For potable water mains, the other way of filling the pipe is to put a smaller pipe inside the main pipe and use that to pump a clean fluid into the pipe and ballast it that way. So you have to calculate how much pipe is going into the bore and how much fluid you want to pump into the pipe, because again, if you pump too much in, you've got heavy pipe hanging out of the ground, and if you don't pump enough in, you've got flotation and buoyancy within the bore. But yes, you can pump a chlorinated or disinfected water into the pipe and ballast it that way. The other way of doing it is to put a heavier fluid in the pipe, put a pipe in the pipe and put a heavier fluid in and try and counter the buoyancy that way. But with these big pipes, once you start getting up to 500 mil pipes, that's a lot of buoyancy. You'd have to have very heavy fluid in there to do that. So there are ways of reducing buoyancy without allowing dirty fluid in fill. Yeah.
Okay, perfect. Next question there. What were the actual settlements versus predicted along the pipeline?
Zero actual settlement. We saw no settlement at all, no vibration at all. As I say, we had a little bit of breakout in the park at Monkstown, which we were able to isolate and clean up. You'd maybe know more than me about the noise, Paul. You were more involved with dealing with the residents and the locals, but I don't think we had much of an issue with noise impact either.
No, there was nothing significant. I mean, you kept within the requirements of the works information anyway, certainly at all times. Even with the late hours that were put in often as well, and there was a couple of overnights as well. I think it was, it was very successfully mitigated with the noise barriers as well. They did work. Yeah.
Very good, excellent. I suppose just two comments there, thanking you for an excellent lecture. So I'll just answer those. And Ger Downing, what's the longest distance that a HDD could be used on?
Well, that 400-ton rig is capable of drilling about 3.5 kilometers. But the issue when you start getting out to very long lengths is it gets harder and harder to steer the drill bit. If you can imagine, you're trying to maybe nudge the drill bit a couple of degrees to the right, but you do that by rotating 3 kilometers of drill string. You've probably got to put 3 torsional wraps in the drill string before you see any movement at the drill bit. So it gets very difficult. So once you get above about 2 kilometers, the technique that we use is to drill 2 bores from either side and they meet in the middle. It's called an intersect project. And then once you've got drill pipe all the way through from one bore to the other and back to surface, you can pull the pipelines in. These long bores, they're only really applicable to steel pipelines, though. The tensile strength of the polyethylene, no matter how much ballast you put in it or how thick a wall you put it, there is a limit to the tensile strength of the polyethylene. So you'd have to go up to a steel pipeline. But 3.5 kilometer drills have been done for steel, oil pipelines and gas pipelines.
Okay, thank you. Justin Dorn, what was the program period for the projects? I suppose the actual construction phase, I suppose, and overall, perhaps, Paul?
Yeah, it was roughly a year from contract signing, with kind of cooling period as well. So it was roughly a year. I think they signed it in April of 2019. It was, well, technically it was signed off in around September last year. You had to kind of add in the COVID delays and lockdowns and that. But there was a separate measure within the contract that the 2 drill pipes themselves was a milestone that they had to be in kind of within 10 months of taking possession of the site, which they were. So that was the kind of the success measure of the project.
Very good. I might combine 2 there just about the bentonite. I suppose one was where was the bentonite sourced from, and then I suppose how was it disposed of, and are there environmental requirements around that disposal?
Yeah, the bentonite was sourced from our regular European supplier, and disposal. Yeah, as I say, we recycle all the bentonite, so we minimize the actual volume of fluid that we have on site, but it was all disposed of under a permitting process with waste disposal notes so that we could keep track of the volumes that were being generated and taken off site. It was all taken away to a licensed disposal site. There are occasions, the bentonite is really just clay and then whatever drilled cuttings come to surface. So provided you're not drilling in contaminated land, there are uses for the bentonite. It is a soil improver. It helps the water retaining capacity of soil. So if you're drilling in very loamy or sandy soils, you can often find local farmers who will take it off you. Unfortunately, dry soil isn't a problem that the farmers of Cork have very often. So there wasn't a local use for it, unfortunately.
Just in Dornan again, how long did it take to pull the pipe through the bore? I suppose, like from the point when you attach it to the rig.
Yeah, it was about 10 hours. So it was beginning to get dark. Well, it was dark. We started the pull about 7, 8 o'clock in the morning, and it went right through into the early evening, late night. Yeah, that was the one time when we felt that it was the biggest impact to the locals. Because once you start pulling the pipe, you can't stop and pick it up again the next day. It's only going in one direction once we start that pull.
Yeah. Have you ever had an instance where there was an issue and you weren't able to pull it? I mean, obviously not in this project, but on another project. That's I don't know, that you've had to literally pull the pipe back out again and ream it out again, or something.
It's very rare. It's absolutely worth spending the time to make sure that your hole is capable of taking the pipe before you start to pull it. And if that means pulling your final hole opener through 2, 3 times, then sometimes that's something we do. But yeah, there have been occasions when the ground has collapsed, or we've had a problem with a rig, and the pipe's got stuck, and we've had to pull it back out and clean the bore out and go again.
I suppose somewhat of a follow-up question there for somebody. Did you have any problems with damage to the pipe during this particular operation?
No, as I say, it came through with a lot less pull than we'd anticipated. There was barely a mark on the outside of the pipe when it came through. It was in really great shape. Having the SDR9 pipe, much thicker walled pipe, it meant that if there was any damage, it wouldn't have been a big issue. But no, the pipe was looking great when it came through.
Okay. Well, perhaps for Paul, why were 2 500mm pipes drilled instead of one larger one?
Yeah, fair question. We actually only needed one pipe for the requirements of transferring the flow. The second one is redundancy, really. There will be times when you switch from one pipe to the other. And also future proofing. We did, you probably won't get a chance to come back and do a project like this in Cobh to Monkstown. May well be required that both pipes are used sometime in the next 30, 40 years and beyond, But ultimately, redundancy was why you keep pipes there.
Question there just about the fault zone. Would an alternative drill heads / teeth have been considered if the issue had persisted? I mean, are there alternative, depending on geology, is there alternative drill heads that can be used?
Yes, yeah. If we'd run into very hard material that was continuous down there, we may well have decided that rather than persevere with the slow ROP or keep seeing wear on the drill bits, we'd have changed the drill bit out for something with smaller cutters that was more abrasive. There are potentially other drill types as well. These were tungsten carbide inserts. You can get drill bits with polycrystalline diamond compact PDC tips, which have much higher wear characteristics, but they're prone to shattering. So they're not so good in broken ground. So yes, there are alternative bits we could have tried had the bit that we selected not got through.
I think possibly you've somewhat answered this one. At what length does HDD become economically viable? I assume for short pipe runs, traditional cut and cover methods would work out cheaper.
Yes, yeah. I mean, it depends on the size of the pipeline. We run 9 rigs in our fleet, everything from 2 men in a transit van that do fiber optic up and down the street, right up to that 400-ton rig that's capable of putting in 42-inch steel pipeline over 3 kilometres. So it's a case of picking the rig for the job. The ground conditions have a big effect. You know, the harder the ground, the slower the drill. But very often, if you're looking at things like potentially traffic management and import of backfill and disposal of excavated waste and potentially contaminated land, if you're looking at all these issues, then directional drilling can be cost effective even on relatively short shots. Probably, you know, even our smallest drills we wouldn't really look at unless it was something very specific at anything less than about 60 or 70 meters, because you just can't get down and back up again in anything less than that.
A question just occurred to me myself. I suppose in terms of other utilities, when you're doing this type of work, I mean, I think we all know that's kind of maps of existing utilities can be aspirational sometimes. Is it the case though that, like certainly with something this size, that you're going so deep that it doesn't become an issue, or are there other things that you can do in terms of, you know, testing and that?
Yeah, there's more and more directional drilling going on these days. It used to be the case where everything else was in the first 2 or 3 meters. And once you got below that, you were clean to go. But as more and more drilling is taking place, you're beginning to run into congested areas, even deep underground. And unless we know it's there, we can't avoid it. There are no sensors in the drill bit that would pick up existing pipelines. There are magnetic guidance systems, so you would get magnetic anomalies if you were drilling close to a ferric body. But of course, if it's a polyethylene pipeline, you wouldn't know you were drilling into it until you lost your drilling fluid.
I suppose on a similar kind of vein, there was the unknown of the key wall in the dockyard. With the piled key wall, we didn't quite know the depth of the piles because there's some, you know, 40, 50 years old, some of these piles, and we kind of had to adjust the design to go under that and then some, but with the possibility that we would actually be going through piles as well. So there's other unknowns. It's not just the utilities as well. In this case.
Yeah. Query from John Mead: is CCTV camera attached to the pipe when it's being pushed through to see if there's obstructions to the borehead?
No,
you're still in the slurry at that stage.
Yeah, you wouldn't be able to get any visualization down there because of the slurry. The CCTV is used to inspect the pipe before it's pulled, but not during the drilling.
Okay. Are there any ground conditions where you can't use directional drilling?
Because we use drilling fluid to support the bore and flush the cuttings out of the bore, we're reliant on a fluid circulation system. So if you're in ground conditions such as very loose, permeable, porous gravels, cobbles or boulders, and your drilling fluid is all disappearing into the formation, it can get very difficult to directionally drill in those kind of ground conditions. Sometimes we set surface casing and isolate these loose grounds at surface before we get into bedrock. If it's only short sections of the bore, it's possible to pump cement or grout down the drill string and seal up these formations before you drill in them. But at some stage that becomes economically unviable if you've got long lengths of drill in cohesionless, unstable, porous, permeable formations.
Okay. Question there from Michael Ryan, perhaps one for you, Paul. Thank you for a very comprehensive presentation. Can you please confirm what the pay and gain share mechanism was and how the early warnings worked out, and was NEC a success?
I suppose I'll start from the end. Yes, NEC was definitely a success in this instant. We closed the project, the final account, say relatively painlessly. It's the work is done before you get to the end, basically. So there's not a kind of a push to get agreements laid out and to be putting claims in the end of a project. There's a time barring mechanism on claims right throughout the project, or any extras, any early warnings, anything like compensation events. They're all dealt with as they arise. You're not kind of laying them off to the end or coming up with a surprise. So in that regard, the NEC was a success. Everyone worked together on the project as well, so it kind of forces that collaboration, bit of a mindset adjustment at times to your traditional contract. And the pay and gain share mechanism, I can't share the details of it because we're still in defects period of the contract, so it still is a live contract as such. So yeah, I mean that'll all become public knowledge in due course, I'm sure. So the early warning mechanism, I don't remember offhand the exact amount of them, but it was relatively low. In many cases, the early warning, that's all it was an early warning. It didn't result in anything in the end. In certain cases, it did raise the target cost. Early on in the project with utility diversion works, that did raise the target cost somewhat, but nothing we didn't allow for within the budgets of the project anyway.
That's good to hear. I guess NEC has had some bad press in Ireland recently, and it's good to hear of a project because, I mean, obviously there's billions, probably trillions of pounds worth of projects have been built under NEC successfully over the years, but it's good to hear where it was successfully completed in Ireland.
On that matter, NEC, like any other contract, there's many variations of the NEC, but it's just use what contract is right for that particular project. In this case, NEC. It's not to say that forcing NEC on every project is the right way to go either, but certainly I'd be happy to use it again. It's very easy to use, administration heavy, but yeah, happy to use it again.
Query there from Dan O'Sullivan. What maintenance provisions for the pipelines were built into the project, for example, pigging?
Yeah, so I'll take that. So yeah, there is pigging chambers installed in the Sand Key on Monkstown site. So it's ice pigging for the maintenance of the two pipelines between the Monkstown and Cobh.
So I know I'm just picking and choosing a little bit. I think you've answered quite a lot of them, kind of duplicates. Might make sense of this one, Ross. Would you have done any directional drilling next to a river that has high tide? I presume, I suppose the question in this scenario, the tides,
yes,
how did it influence it, or did they?
Yes, we have. We're doing one at the moment, drilling parallel to the Thames in London on a tidal stretch of the Thames. I guess the question relates to groundwater again. Generally speaking, the drilling fluid within the bore is maintained at a higher hydrostatic pressure than the surrounding groundwater, so you can deal. The pressure of fluid within the bore prevents any ingress of groundwater except in exceptional circumstances. I think what was happening during Storm Ciara and Storm Dennis at Monkstown was that the groundwater rose significantly above the level at which the fluid was able to keep it out. It was flowing in over the top of the fluid, if that makes sense, and getting into the bore stream very close to surface. I mean, you could see when you looked in the drill pit, you could see fresh water flowing in streams into the drill pit. So it wasn't getting into the bore at depth and mixing with the fluid on the way to surface. It was coming in just below surface. So that's why it was so difficult to control there. But drilling next to rivers with that are tidal with groundwater levels that rise and fall, on a 12-hourly basis. No, we've done that, and that's generally not an issue. We do a lot of marine crossings as well. We drilled the Menai Straits between North Wales and Anglesey under the marine channel there. We've done a couple of islands in Scotland drilling marine channels that are entirely under saltwater environments. and outfalls to both discharge of effluent and as landfalls for cables and fibre optics coming in from offshore wind farms and the like. So that's not a concern.
Good. So look, I might just take one final question. There's a few there, but I think most of them are repeats, and I have two there that are quite similar. I suppose I'll merge them into one question. What method is used to map the final route of the pipeline, and were tracing strips installed in the pipe?
No, tracing strips aren't installed in the pipe. We use the pilot hole string or the guidance. The guidance system is a ring laser gyro, so it's very accurate. But we use the pilot hole bore path as the as-built for the drill. When you're drilling in bedrock like that, the hole openers will always follow the pilot hole string. If you're drilling in very soft materials, then it's not unknown for the hole opening operation to key seat and drill out of the side of the pilot hole rather than follow the pilot hole. And if that's a concern, we can always run a guidance system through the bore once it's been piped. But it wasn't a concern on this project.
So look, as I say, I might just draw to a close there. I again would like to thank Ross and Paul for an excellent lecture on a very interesting topic, perhaps for Cork, a once in a lifetime project. Unfortunately, I suppose one of the benefits of the virtual environment is that we've reached out to a quite large audience. I think I saw somewhere around 250 people online at one point, but unfortunately we can't give you the traditional round of applause that we would have in an in-room lecture. But I think just looking at the chat screen there and the Q&A, there's lots and lots of people thanking you for an excellent presentation, and I'd add my thanks to you for that as well.